this time when it's this far away from me. More space for more bedroom. And whatever. We'll pay special attention to the ideal gas because it's one of the simplest types of method to understand how the heat works in matter. Using our knowledge of momentum and kinetic energy, will relate microscopic processes of an ideal gas to the microscopic behavior of its individual molecules. We'll also use microideals to understand the heat capacities of both gases and solids. Finally, we'll take a look at the various phases of matter, gas, liquid, and solid, and the condition under which each occurs. We begin here. In liquid, the intermolecular distance are usually only slightly before to learn the method. I would like to tell the difference between the gas, the liquid, and the solid in a microscopic way. As you can see here, in gas, the molecules move nearly independently, which means the molecules for gas now with a long distance and almost have no interaction with each other. However, for liquid, they're closer. There is some interaction between them. However, this interaction is vulnerable and there can be some variation, and the displacement of the molecules is very easy. The interaction between them is larger than the gas. However, it's not so large to restrict the movement of the molecules. Then, in a solid, the molecules even closer, and the interaction between them are so large to restrict the movement of the molecules. In this case, you will see in a microscope both the gas and the liquid, the volume, the shape of it can easily be changed. Especially the gas, it has no specific shape. For liquid, you can see it flows all around. However, for solid, you always see that it is stubborn and it is stable in shape. Then, the one difference between them is the interaction of molecules that consist And the second difference is the distance of molecules. Between molecules in the three kinds of phases, the molecules of gas has the largest distance. And the liquid, in the middle one. For solid, the distance are even closer. dg larger than, much larger than here, and much larger than this. And why we have to know this before we are learning? Because there is an interesting result about it. For a bottle of stones, and a glass of sand. If the glass of stone has a volume of large A, and the glass of sand assumes a volume of B, when we mix the A and B, the mixture of the stones and the sand, the volume of it will equal to the addition of A and B. Of course not, because the sand can enter the space between stones. Thus, the volume of it will smaller than the volume of A, the addition of A and B. And a similar thing happened for liquid, happened for gas, because with different kinds of liquid, the distance between molecules are different, similar like the stones and the sand. And here is the video. Wait a second. The glass of water. Then we add some alcohol. that is a full glass of mixture of water and alcohol. Then shake the glass to make them mix more uniform. Do you see that? Okay. After the mixture, you will see the volume of the mixture of water and alcohol decreased. Similarly, the mixture of stones and sand, which means the distance between molecules for different kinds of liquid are different. When they mix, the different molecules will enter the space between molecules because different distance means there are some space between them. And the distance between them is so large we can see it. Then we got to know what exactly it is for gas, for liquid, and solid. Then we're going to learn the first one, some vulnerables for gas, because that is the easiest way to learn the heat energy inside it. The conditions in which a particular material exists are described by physical quantities such as the pressure, the volume, the temperature, and the amount of substance. For example, a tank of oxygen in a welding outfit has a pressure of the release gauge and the label stating its volume. We could add a thermometer and place the tank on the scale to determine its mass. Those vulnerables describe the state of the material and are called state vulnerables. For gas, the most used state vulnerables: P for pressure, V for volume, N for the amount of substance in mole, R, T, temperature. For the temperature, it is important to remember always use the temperature in Kelvin, because that is the international unit in Kelvin, not in the centigrade. The volume V of a substance is usually determined by its pressure P, temperature T, and the amount of substance, described by the mass M total or number of moles N. We are calling the total mass of a substance M total because later in the chapter we will use the small m for the mass of each molecule for one molecule. In a few cases, the relationship among P, V, T, and N is simple enough that we can express it as an equation called the equation of state. Here is a simple equation of state for solid material. The first one, V is actual value times the V0 is the volume of it before the treatment, or its volume in origin volume. Then times the large square 1 and beta. The beta is the temperature coefficient of volume expansion. Is the fraction volume change per unit temperature change. Briefly, the volume change caused by the temperature. The beta is a constant related to the change in volume caused by the temperature. Then another constant, K, briefly, that is the volume, that is a change in volume caused by the pressure. As we know, some material always expansion when the temperature increased. Therefore, there is a positive for the beta. And the constant related to the pressure, also naturally, the large pressure is on something, no matter it is a solid or a liquid or a gas. The large pressure, the small volume it is. Therefore, the constant K, there is a negative before it, to show the change in the pressure is the smaller its volume it is. However, it is an equation, but it's not so useful. That is an ideal equation. We have just to have a view of it. The volume is related to the temperature, also related to the pressure, no matter it is solid or liquid or gas. Then we put more attention to the gas, the ideal gas. First, from the beginning, we study the gas is according to an experiment, the setup for study the behavior of gas, which is variable volume with variable pressure and with variable temperature. And the number of gas molecules in the cylinder also can be changed by the gas source. And by change those state variables, we find some conclusions. The first one is the volume is proportional to the number of moles. If we double the number of the moles, keeping pressure and the temperature constant, the volume doubles. And the second one, the volume varies inversely with the absolute pressure P. If we double the pressure, we are holding the temperature and the number of moles in constant. The gas compresses to 1/2 of its initial volume. In other words, the production of pressure and the volume equals to a constant one, when N and the temperature are constant. And the third one, the pressure is proportional to the absolute temperature. If we double the absolute temperature, keeping the volume and the number of moles constant, the pressure doubles. In other words, P equals to a constant times the temperature, when N and the volume are constant. Those three relations can be combined neatly into a single equation called the ideal gas equation. PV equals to nRT, where R is a proportionality constant. This is the most important equation in this chapter, or in the overall chapter of the more PV equals to N pressure, volume, number of it in mole, and the constant, and the temperature. Temperature in K, An ideal gas is one of which equation holds precisely for all pressures and temperatures. This is the idealized model. It works best at a very low pressure and high temperatures when the gas molecules are far apart and in rapid motion. Because even though the molecules of gas, the distance between them are so large, however, we ignore the interaction between the molecules. In fact, or as a matter of fact, there is some interaction between them. Maybe small, but there is some little interaction. So, in this equation, we ignore the interaction, and that is the ideal gas equation. For an ideal gas, the interaction can be ignored, but in nature, it cannot. We might expect that the constant R in the ideal gas equation would have different values for different gases, but it turns out to have the same value for all gases, at least at sufficiently high temperature and low pressure. It is called the gas constant, and it can be written by if you remember, that is with the same unit of the heat capacity in mole. We can express the ideal gas equation in terms of the mass and total of gas using the overall mass can be obtained by the production of the number of the molecules in mole times the mass of one mole of the molecules. An example of that is 18 grams per mole for water. From this, we can get an expression for the density rho equals to m total divided by V of a gas. A new equation is PV equals to m total divided by constant RT. Rho equals to T. No matter how to write it, it is began from the ideal gas equation. Began from the PV equals to nRT. Just we have translated the n by m total or m total divided by RT. But the meaning of these two equations equals to each one, equals to this one. for constant mass, which means the mass of it and the number of molecules of it is a constant. When we name the P1, V1, and M1, and the T1 for materials A, and P2, V2, and N2 are T2 for B. When the number of it or the mass of it is constant, we do a derivation for P1, V1, P2, V2, Y, N1 R, T1, and 2 R, T2. If the mass are constant, which means the N is a constant, N1 equals to N2, then the R is always a constant. And the final result, only the P, V, and the T is left. You can write like this, or do a translation by P1, V1, T1 equals to P2, V2, P2. You may find it boring, however, that is a very useful equation because it describes all the three conclusions in one single equation. When we do the calculation, it is very easy to use. There's a choice question. If a volume of an ideal gas is double, well, its temperature is 4 times. That's the pressure A, B, C, and D. Volume double, temperature quadruple. Can you tell me the answer? That's the pressure. Ideal gas is double. Pressure. If you remember the equation here, before the variation in volume and temperature, that is P1, V1, P0, V0, and T0. Then the volume doubled and became 2V0, and the temperature quadrupled 4 times 4 T0. If that should be equal, the final pressure should be increased by a factor of 2. State before the change. 1, the constant is equal, or the mass is a constant. Use the equation here. Then a container holds 0.5 meter square of oxygen at an absolute pressure until the pressure drops to 1 atm. If the temperature remains constant, what new volume does the gas occupy? Okay, we can draw it. Holds 0.5 of oxygen at the absolute pressure of 4 atm. 4 atm. That is the pressure. And 0.5 meters square is the volume. The valve is open, allowing the gas to drive a piston, increasing the volume of the gas until the pressure drops to 1 atm, which means before the variation, the volume increases and the pressure drops to 1 atm. 1 atm. How about the temperature? If the temperature remains constant, T0, and finally T0. At the beginning, T is unknown, V is known, and P is known. After the variation, T is unknown, V is unknown, and P is known. How to do the calculation? Is the mass of the volume changed? No. If not changed, we can use this equation. Before the variation, the pressure of it is 4 atm, and the volume of it is 0.5 meter square divided by the initial temperature. Unknown. They are equal to the state of it after the variation, and the pressure will become 1 atm times the volume, what is we want to know. And the temperature, yes, T0 is unchanged. Therefore, we can erase the temperature for both sides. Then yes. So the final result is exactly 2 meters square. The proportionality of pressure to absolute temperature is variable. In fact, in above chapter, we define the temperature scale in terms of pressure and in a constant volume gas thermometer. They may make it seem that the pressure-temperature relationship in the ideal gas equation is just a result of the way we define temperature. But the equation also tells us what happens when we change the volume or the amount of substance. Also, the gas thermometer scale turns out to correspond closely to a temperature scale that does not depend on the properties of any particular material. Here is a picture of how we define the temperatures. At 0 centigrade, or we can say 273 Kelvin, the pressure at the freezing point of water, or the temperature of the mixture of water and ice. Then the temperature increases all the way to 100 centigrade, or 373 Kelvin. The pressure at the boiling point of water is much higher than the mixture of the water and the ice. In this figure, you can see the interaction or the variation of the pressure influenced by the temperature. The pressure increases all the way with the temperature increase from 0 to 100 centigrade. explicit citrate states. Otherwise, you can use the ideal gas equation for any situation in which you need to find the state of a gas. Ideal gas equation. Which one? This one. No matter how many equations has been obtained, it comes from or it is based on the ideal gas equation as shown here. The problem, when you want to solve a problem, you can use the following steps. The first, identify the target variables, the pressure, or the volume, or the temperature, or the mass. In some problems, you will be concerned with only one state of the system, in which case PV equals to nRT is the relationship to use. Some of the quantities in this equation will be known, others will be unknown. Make a list of what you know and what you have to find. And third, in other problems, you will compare two different states of the same amount of gas. Decide which is state 1 and which is state 2, or you can say the state, the initial state, and the final state. And make a list of quantities of each P1, P2, V1, V2, T1, T2. If all but one of those quantities are known, you can use the equation here. P1, V1 beyond T1 equals to P2, V2 beyond T2, and equals to a constant. Otherwise, use the ideal gas equation, PV equals to nRT. Finally, some problems involves the density rho, mass, per volume, rather than the number of moles and the volume V. In this case, it's most convenient to use rho equals to Pm beyond RT. Or you can make it easier. You can do the translation by yourself. For example, there's the content and the gas molecules inside. If we know the volume of it, and we know the density of it, mass per volume, like 1 gram per meter square, 1 kilogram, and the volume we can give a number of 2 meters square. It is not necessary to remember all the equations. If the rho is known, the V is known, we can calculate the mass of all gas molecules in it, and it can be calculated by the production of rho and the V, and the final result can be 2 kilograms. 2 kilogram gas molecules inside the container. Then mass is known. How can we know the number of it? We just do the division of the mass of it by the mass of 1 mole gas molecules, the large N. We have already learned, for example, for oxygen, the mass of the element of each element in oxygen we can divide it by or we can, if you don't remember, you can check on the internet. 2 grams or more. And the final result, again, the gram erased with each other. 2000 divided by 32 more. Okay, we got to know the number of the gas molecules inside the container according to the rho or the density of it. Therefore, no matter which one is given, the mass is given, or the number of it is given, or the rho of it is given, they can be translated with each other. And which means you don't need to remember this. Lots of equations. The most important one, PV equals to nRT, must be remembered. And the volume of the R must be remembered. M total equals to N and times the mass of it of one or more of the molecules. You're familiar with this equation? That should be learned in your chemistry. Of course, no? No? If no, then pay a little attention on it. Similar, just use the transformation. And the rho don't need to have a remember. That it is useful, but you also don't have to remember it because it can be obtained from the ideal gas equation. Briefly, I will remember of number 1, 2, and 3. Those 3 important equations. Okay, the next class we are going to do some